The Cauchy Schwarz inequality is a special case of Holder inequality, which depends on this lemma. Given 1 over p plus 1 over q equals 1, so p and q are both greater than 1, for any real positive a and b, a to the p over p plus b to the q over q is greater than or equal to ab, and they're only equal if a to the p equals b to the q. Weird little fact. We subtract this over, we're trying to prove that this quantity is greater than or equal to 0. So we take its first derivative and its second derivative. Since this is positive and this is positive, this function is concave up for all values of a. So it only has one minimum, which occurs here. A to the p minus 1 equals b. We go and we plug that in to find out what the minimum value is, and we hope it's 0 or more. A to the p over p plus a to the p minus 1 raised to the q over q minus a times a to the p minus 1. Now, weird consequence of the choices of p and q. 1 over p plus 1 over q equals 1 rearranges into p is pq minus q. In other words, a to the p minus 1 times q is a to the p. When we simplify that, we have a to the p, a to the p, a to the p. Pull it out. 1 over p plus 1 over q minus 1, but we know that's 0 by design. So the minimum value is 0. And it is only achieved when a to the p minus 1 equals b. If you raise both sides of this to the q power, we use that weird little trick again, and we get a to the p equals b to the q, the rest of the theorem. I hunted for an easier way to explain that, but this argument from Casella is the best one I found.